Hi all the students. Today we are going to study cyclic redundancy check, which in short is also known as CRC. So CRC is another method for error detection. So basically a sender transmits the data frame or the message and it is received by the receiver. So the generation of CRC, that is the cyclic redundancy check, is generated at the sender side. So basically CRC generation is the responsibility of sender side. So the sender is responsible for generating the CRC code. Now the CRC code or the cyclic redundancy check is also known as polynomial code. Basically in this method, the bit strings are treated as representation of polynomials. That is why it is known as the polynomial code, because the bit strings, the collection of zeros and ones, are treated as representation of polynomials where the coefficient would only be zeros and ones. Since we are not talking about any integer numbers, we are talking about binary numbers. So if we are treating the bit strings of binary numbers as polynomials, so it is quite obvious that the coefficients would be either 0 or 1. Now if it is a k-bit frame, so k-bit basically signifies the size of the frame, like k could be any number like 6, 5, 4, 8, anything. So if it is a k-bit frame, then it is regarded as a coefficient list for a polynomial with k terms ranging from x to the power k minus 1 to x to the power 0. And such a polynomial is said to be of degree k minus 1. The next bit is the coefficient of x to the power k minus 2 and so on. Now I'll explain it through an example. For example, 110001 is a bit string. So you can see that it has 6 bits. Therefore, I can call it a 6-bit frame. So this 6-bit frame is then regarded as the coefficient list for a polynomial with 6 terms, which would be ranging from x to the power 6 minus 1 to x to the power 0, right? So if I convert it into a polynomial, it would be like x to the power 5 plus x to the power 4 plus x to the power 0. How? See, if I consider this bit string 110001, so starting from the least significant bit, which is also known as LSB, till the most significant bit, also known as MSB. So I'll start from the least significant bit. So it starts from, this is the 0th bit. This one is the 0th bit. So the coefficient is 1 into x to the power 0. Then this is the first bit. So the coefficient is 0 into x to the power 1. This is the second bit. So coefficient is 0 into x to the power 2. This is the third bit. The coefficient is 0 into x to the power 3. Then this is the fourth bit. The coefficient would be 1 into x to the power 4. And this is the fifth bit. So it would be, the coefficient would be 1 into x to the power 5. So anything we know multiplied by 0 gives us 0. So hence we do not have x to the power 1, x to the power 2 and x to the power 3 here. Rest we have x to the power 5, x to the power 4 and x to the power 0 over here. So this is the polynomial that has been generated out of this bit string, right? So this is how you generate a polynomial when you are provided with a bit string like this, where of course the coefficients would either be ones or zeros. Now both sender and receiver must agree upon a common divisor, which is also known as the generating polynomial denoted by gx. In a common language we call it divisor, and otherwise we call it generator polynomial denoted by gx. Alright, so before the CRC is performed, both the sender and receiver must agree upon a common divisor. Both the high and low order bits of the generator polynomial must be 1, right? So the high order bits is known as the most significant bit and the low order bit is known as the least significant bit. So that means the LSB or the least significant bit, and the MSB or the most significant bit here must be 1. So you can clearly see that the LSB is 1 and the MSB is also 1. So this is one compulsion, that both the LSB and MSB must be 1. And the frame must be longer than the generator polynomial or the divisor. So the divisor, the common divisor which both the sender and receiver will be using, it should be less than the frame, or in other words, the frame must be longer than the divisor or the generator polynomial. Now, how do we generate CRC at sender side? So the task of generation of the CRC is the responsibility of the sender. So how it is done at the sender side, that we will see. There are some steps for that. So the first step is that, first of all, you have to find out the length of the divisor. Now when you are given a question wherein you have to generate CRC, you will be given the bit string of the frame and you will be provided with the bit string of the divisor, right? So all you have to do is that with the divisor that you will be provided with, you have to find the length of the divisor. How will you do that? By counting the number of bits in the divisor. After that, in the second step, append L minus 1 0 bits to the original frame. So L is the length of the divisor. So you have to append L minus 1 0 bits to the original frame. So say for example, if the length of the divisor is 5, that means 5 minus 1, 4 0 bits will be appended to the original frame that you are provided with. After that, perform the binary division. That means divide the frame by the divisor that has been provided. But after appending L minus 1 0 bits to the original frame, to this frame, you will then perform binary division. That means you will be dividing the frame appended with L minus 1 0 bits by the divisor. Okay, so after the binary division, the remainder that you get is known as the CRC. Again, one thing that should be kept in mind is that CRC must also be of L minus 1 bits. So if your divisor is of 5 bits, then the CRC must be of 4 bits. Now to perform binary division, you must know exclusive OR operation. This you'll get to know once I explain this the binary division through an example. So as of now, you must know what XOR operation is, right? Which is also known as exclusive OR. So if I take two values A and B, so their XOR will be like A will be 0 0 1 1 and B will be 0 1 0 1. So A exclusive OR B would give you, in case of exclusive OR, with the same binary digits you get 0, and with different binary digits you get a 1. So if both A and B are 0, you get a 0 as the result. If A is 0 and B is 1, then you get 1 as a result. If A is 1 and B is 0, you again get 1 as result. And when A and B both are 0, then you get 0 as the result. So you have to keep in mind that for the exclusive OR operation, when both the bits are same, you get a 0 in result. And when both the bits are different, you get a 1 in result. Now we'll see the use of this exclusive OR in our binary division operation. Okay, so in the question basically, you'll be provided with a frame and the generator or the divisor, right? So we'll see how the CRC is generated at the sender side. So this is a frame. We have total 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have total of 10 bits in the original frame, and the divisor or the generator has 1, 2, 3, 4, 5 bits. So in the question, you will be provided with the bit strings of the frame and the bit strings of the divisor like this, right? Now you can clearly see that there are 5, the length of the divisor is 5. That means you have to append L minus 1 0 bits to the actual frame. So that means you have to append 4 0 bits to the actual frame. So the frame or message after appending 4 0 bits is like this. It is 11 0 1 0 11 0 11 and 4 zeros. Now this message. After 4 0 bits have been appended to it, this message is divided by the divisor. So you can clearly see that the first 5 bits here are 1 1 0 1 0. So we look at the most significant bit. So here the most significant bit is 1, so we need a 1 here. So I divide the divisor by 1 and I get 1 0 0 1 1, right? Now we will perform the exclusive OR operation. 0 and 1 will give you a 1, 1 1 will give you a 0, 0 and 0 will give you a 0, 1 and 0 will give you a 1, and 1 1 will give you a 0. We will discard this bit and we will bring this bit down. So now it becomes 1 0 0 1 1. So again the most significant bit is 1 here. So we will multiply the divisor by 1 to get a 1 here. Now when we multiply 1 0 0 1 1 with a 1, we get 1 0 0 1 1 here. Now again performing the exclusive OR operation, 1 and 1 gives you a 0. Again 1 1 gives you a 0, 0 0 gives 0, 0 0 again gives 0, and 1 1 gives a 0. Again I discard this bit and I bring this bit down. So now you can see that the most significant bit is 0, so I need a 0 here. Hence I will multiply the divisor by a 0 and I get 5 zeros over here. So 1 and 0 gives me a 1, 0 0 gives me 0, 0 0 gives a 0 again, 0 and 0 gives a 0, and this 0 and 0 also gives a 0. Now I will discard this 0 and bring this 0 down. Again the MSB is 0 here, so I will multiply the divisor by 0. So again in the result I get 5 zeros. After performing the exclusive OR operation, I get a 0 here, 1 here, 0 here, 0 here and 0 here. Then I again discard this bit and bring this 1 down here. So again in the MSB you can see there is a 0 here. So I will multiply the divisor by a 0 and then I again get 5 zeros here. 1 0 gives me a 1, 0 0 gives me 0, 1 0 gives a 1, 0 0 gives a 0 and 0 0 again gives a 0. I discard this 0 bit and I bring this 1 bit down. Now again if I look at the MSB, it is 0. So that means I multiply my divisor by 0. So again I get 5 zeros here. Now 1 and 0 gives me a 1, 1 0 gives me a 1, 0 0 gives me a 0, 1 0 gives me a 1 and 0 0 gives me a 0. Again I discard this bit and I bring this 0 bit down. Now you can see that the MSB is 1. That means I need to multiply the divisor with a 1. So I multiply the divisor with a 1 and I get 1 0 0 1 1 here. So now 0 and 1 gives me a 1. 0 and 1 gives me a 1, 1 1 gives a 0, 1 0 gives a 1, 0 0 gives a 0 and 1 1 gives a 0. Again I discard this bit and I bring this 0 bit down. Now you can see the MSB is 0 here, so I need to multiply the divisor by 0 and then I get 5 zeros again. So 0 and 0 gives me a 0, 1 and 0 gives me a 1, 0 0 gives me a 0, 1 0 gives me a 1, 0 0 gives me a 0. Again I discard this bit and I bring this 0 down. Now since the most significant bit is 1 here, so I will multiply the divisor again by 1. So I get 1 0 here, right? 1 0 0 1 here. Then performing exclusive OR, I get 1 1 1 0 0. Then I bring this last 0. This last 0 I bring it down and I get, what do I get? I get 0 1 1 0. This 0 you know is discarded. So since the MSB or the most significant bit is 0, so I multiply the divisor by 0 and get 5 zeros again. So performing the exclusive OR, I get 0 and 0 gives me a 0, 1 0 gives me a 1, 1 0 gives me a 1, 1 0 gives me a 1 and 0 0 gives me a 0. Again I will discard this 0 bit and what am I left with? 1 2 3 4, 1 1 and 0. So I am left with 4 bits, which is 111 and 0, and this is the remainder of the binary division, and this remainder is known as the CRC. Now remember, I said the length of the CRC should be equal to L minus 1 bits. So the length of the divisor, which is L, is 5. So I am getting exactly L minus 1. That is 5 minus 1, which is equal to 4 bits. 1, 2, 3, 4. So this is my CRC. 1110 is my CRC code. Right? So this is how you find out the CRC. Now, I know that my CRC has been generated. This CRC 1110 is now appended to the original frame. Right? So the original frame, as you know, is 1110111111. Right? Now I will append this CRC, which is 1110, to this frame. And after appending 1110 to this frame, what I get is this. 1101011011 and 1110, out of which these 4 bits are the CRC and this is the actual frame. So this frame, after appending the CRC, is then transmitted by the sender. So this is what is done at the sender's side. Now let's look at what will happen at the receiver side after this frame appended with the CRC is transmitted to the receiver. Now, at the receiver side, how is the error detection using CRC done? Right? At the sender side, the CRC was generated and it was appended to the original frame. But we'll see that how the error detection is done using the CRC at the receiver side. So receiver received the frame which was appended with the CRC bits. So this is the frame which the receiver received, out of which the last 4 bits were the CRC, right? Now, as I said, both the sender and the receiver must agree upon a common or same divisor. So that means same divisor will be used at the receiver side also, which is 10011. Again, binary division will be done in the same manner. The only difference here is now that at the receiver side you have 1110 appended to the frame instead of 4 zeros, right? So that means the result of binary division will vary now. So we will do binary division in the same manner, that is the actual frame appended with the CRC bits, but the divisor remains the same. The frame, last 4 digits of the frame have been changed, but the divisor is same. And after we perform the binary division of the frame appended with the CRC by the divisor or by the generator, then the result we get is 5 zeros. So this is the remainder, right? So the binary division will be done in the same manner as it was done in the sender's side. So you know the method now. So I will just show you the remainder. So this is the remainder that we get after doing the binary division. And the remainder you can see here is 5 zeros. So basically I can say that the remainder is 0. So if remainder is equal to 0, then you can conclude, or then the receiver can conclude that the transmitted frame is correct. That is, there is no error in the transmitted frame. So this is how the receiver can detect the presence or absence of an error in the frame sent by the sender.